So hello, yeah, thank you very much for coming. So today we have Professor Andrea Banzatti, and I'm very proud that he's able to connect today from Texas. So Andrea made his. Let me just do this maybe like so. Then we see him also. So he's from Italy. He started with a master thesis in Milano, 2009 with Leonardo Testi. Maybe somebody knows him. Then he did his PhD at the ETH Zurich in Switzerland with Michel Meyer, also a big name in this business. And then he moved on with 2 postdocs in the US, so in Baltimore and Arizona, until he got his permanent position now, hopefully it's permanent, as an assistant professor at Texas State University since 2019. And Andrea is well known in the community as an expert in high-resolution spectroscopy as it comes to observation of protoplanetary disks in particular. So he worked with Dryas a lot, and also there's a Hawaii telescope iShell called. So that's also one of his pet observational platforms, I think, but also with space telescopes like Spitzer, and in the future certainly JWST. So Andrea is particularly interested in molecules, in the disk structure, what we can learn from observations, and this because of the energy range. So it's infrared. It's like maybe 0.1 to 10 AU. So we are looking now at the inner disk. And so we will learn more about that. You see the title also about winds there, which are launched at these distances. And he's also, I mean, I came in contact with him because I think we have a similar philosophy that in order to learn really something about the nature of the disk, we have to really get together several observational platforms, wavelengths, kinds of observations, images, whatsoever, SEDs, line profiles, ALMA, you name it, because all of these observations only allow a certain aspect of the disk, and it's a very challenging task to put this all together. But today we will focus really on the inner regions, and last but not least, he has now put together this spectroscopy of exoplanet forming disks, SPXO disks, and where I'm sure we will hear more about that. And that's of course it's an amazing tool. It seems so there are more than 1,000 expertly reduced infrared spectra for us to play with, to look at, to fit if we want to. And that's also a reason why I invited him. So Andrea, over to you.
Thank you, Peter, and thank you for this invitation. I would have liked to be there in person, but it's not so easy from Texas to come there for one day. And thank you for accommodating the time to make it later. I know that for some of you it's harder. So again, thank you for helping me to be ready, not too early in the morning, but at this time of the day. In my talk, so I'm an observer and I love data. So I will bring you with me on a journey mostly on data and the beauty of data, spectroscopy, infrared spectroscopy in particular, and what we have learned in the past 20 years. So you see my opening slide, I set the stage. I show you some of the higher resolution spectra that we observe from the ground, and I'll talk about that. And I show also some of the, these are models for space spectroscopy with JWST and Spitzer, and I'll cover that. And here you see a gallery of instruments, of observatories that I've used in my research. So in this talk I decided to focus a little less on winds and more to give, the beauty of colloquia is to give a broader story, a broader introduction. So I will start with a broader introduction oops, let's see. Okay, but I want to introduce you to our Texas team, Texas State team. These are our students here at Texas State University, and in particular, highlight a few that are connected to the work that I will show today. Jose Perez, Michael Sanchez, Kirstin Abernathy, and Anusha Kalyan. Anusha is a postdoc, the others are master students, and we also have undergraduates. We don't have a PhD program here at Texas State University. We have a master and undergraduate. Okay, so yeah, so the fundamental question is where we come from. That's why we study disks, and in particular inner disks. So this actually a little story. This is one slide that I put together for my, I believe, my master thesis back then. Just the big question from how do we get a pearl, a beautiful pearl in space, in the universe, in our solar system as the Earth, from protoplanetary disks. These structures of gas and dust that are formed during star formation. They are the standard process of star formation, from molecular clouds that are cores that collapse and flatten on rotating disks that are feeding the star, and a new star is formed. But in the disk, planets are formed. And this is an artist illustration that for many years we used. Now we don't use artist illustration anymore because we have beautiful images of disk, and I will show many of them. So the story of protoplanetary disk and exoplanets is tightly connected if exoplanets form in protoplanetary disk, and this story is set into these beautiful regions in space that are like this one, the Orion star forming region. This is one of the best images taken by Hubble. And it's a very recent story. So we had a lot of progress in the past few decades. So really the first images of disks were taken in around 1984. And this is the first publication where you see occulting the star with a coronagraph. These images were showing this scattered light from the disk. And that paper is beautiful. If you read, you will see that they say, given that this structure is flattened around the star, it reminds us of how flat our solar system is. So it's possible that the two things are connected. And now we obviously know that it is. Now the planets are formed in these flattened structures, rotating disks. At that time, we only knew of our solar system. So we were wondering how the solar system came to be. But 1995, then the first discovery of an exoplanet, and then the big revolution of the exoplanet field. Just a few years later, a new revolution in protoplanetary disks from these very rough first images in the 2000-2010, both Hubble and ALMA. ALMA is an interferometer. Actually, this is not ALMA yet. Interferometry from the ground, the VLA and the SMA. These are arrays of telescopes that observe a millimeter wavelengths. They observe dust emission, and they get very high resolution. And they were obtaining images of disks that in the optical, you see they look like a dark silhouette. You see, similar to the previous artist impression, there is a dark silhouette made by the dust, and then this scattered light from gas and particles, dust particles at the surface. The star is occulted at the center. And with ALMA, instead, this blob, not ALMA, sorry, with interferometry, these blobs of stuff that are of size of 100 AU, 100 and 150, and that were imaging the dust distributed in these disks. And then the big revolution from the Kepler mission, from the exoplanet side. Since 2009, now we know that there are thousands of exoplanets with big consequences in our understanding of the solar system too. And in parallel, since around 2012, 2015, we are now, the big revolution in protoplanetary disk imaging has been to see that disks are not these pixel-like structures or blobs, but include an amazing amount of structures, fine level structures, and even some of them spirals. This looks like a galaxy, but it's a protoplanetary disk. And yeah, the excitement of seeing that these disks are not monolithic and smooth structures, but are highly dynamic and include a lot of information related to evolution of the disk. So this is one of the big revolutions from the protoplanetary disk side. On the exoplanet side, now that we put together detections, this is a plot that is a few years old, but already makes the point. Then if you compare exoplanet detections in this plot with the planet mass and the semi-major axis, and you compare with the solar system, you see that we are sort of alone. We are sort of a rare species, rare solar system. But the fact is that our observing techniques are very incomplete in the region where the solar system is. So now the new instrumentation is pushing this limit to this side, okay? So going toward the solar system, and everybody wants to get to be able to image and detect planets in our parameter space of our solar system. And yet, the discoveries of exoplanets so far already demonstrated that solar systems in general look very different from our solar system. There are hot Jupiters. This was the very first detection, 51 PEC-B. There are warm Jupiters. But even more strangely, there are these planets that are now called mini Neptunes or super Earths that are more massive than Earth, but are much closer in. So if you consider that and these are the most abundant planets in the universe as far as we have found so far. So if you compare with the structure of the solar system, the most common type of planet in the universe is in an orbital region where we have nothing in the solar system. And this is already astounding. So the questions that we had several years ago, where do we come from? Now they become even broader. Not only how do we get an Earth and the solar system from a flattened structure of a protoplanetary disk, but how do we get the huge diversity of planets? Here, some artist impression, because we are not there yet to image exoplanets at this level. So we still have to rely to the creativity of artists here for exoplanets. But the question is even broader. So how do we get these solar planetary systems that are so different from ours and so diverse? And I like to report a quote from a paper by Ice Mulders in 2018. There was a sentence that really struck me there. They were studying the location of the innermost planet in exoplanets in general compared to the solar system. And they stated these results reinforce the view that the solar system is not a typical planetary system, but an outlier among the distribution of known exoplanetary systems. This is kind of a strong statement. So I like to remind myself of that, because we live in exciting times to understand that. So let's zoom in a bit more on the inner regions of protoplanetary disks as the birthplaces of planets. So the long-standing paradigm for planet formation includes three main steps. The dust distributed in the disk first has an early growth of sticking and coagulation, these submicron grains that stick together and grow enough to become little pebbles. And then there is a midlife growth of gravitational attraction, where planetary cores are attracting smaller bodies. And then the late growth of gas sweeping. Planets are potentially forming these gaps that we see in the ALMA images and accreting their atmospheres. So these are very coarse steps to tell the story, from the smallest scales of these solid bodies all the way to a planetary size. And there are regions in disks that are very special in this story, and especially one of those is called the water snow line. It's the distance from the star where the temperature in the disk is either low enough at larger distances or high enough at smaller distances to change water from vapor to ice. So closer distances, the disk is hot, so the water will be in gas form, in vapor. And beyond that, the ice line or snow line, it will be in ice. Now, this special location has a connection also to a step in the planet formation story that has become very much more focused recently, which is called the pebble accretion. So now we know that disks are not static. So it's not just a static structure where there is a temperature gradient, but there is also the solids, as soon as they grow enough to drift into disks, they will drift on large scales and bring ice from the outer regions all the way to the inner regions, enriching the inner disk with vapor. And there is a lot of work that has been growing. Again, this is really frontier research now to study the connection of pebbles that are feeding planetary cores and at the same time enriching the inner disk with molecules, with oxygen from the outer disk. So this large-scale drift of pebbles has, in addition to enriching the inner disk with volatiles, with oxygen, has another important consequence, that it will shrink disks from the large sizes that we see in ALMA images like this, all the way to very small sizes. And I'll show in a future slide how they will look. So this location, the snow line, and pebble accretion have strong consequences, or are expected to have strong consequences on the composition and the size of planets. If they form outside of the snow line, there will be more solid mass increased by ice. They will form larger cores. If they form inside of the snow line, they will be water poor and smaller. There is less solid mass to form them. And this has been proposed early on, but also taken recently by Morbidelli as connected to the big dichotomy in our solar system planets: small planets, rocky planets inside of the snow line, and large giants outside. So what, and the whole picture is complicated by the presence of winds. Again, I will not spend too much time on winds today in this presentation, but I will keep mentioning winds as we go along with the story. And so now, while all of this is happening in planet formation, in the meantime, we know, we observe, and I'll show some observations of winds that are dispersing the inner disk and launching gas into space. So what do inner disk hold for us? They hold, they show us the chemistry of planet-forming regions, and they show us how dust and gas evolve as a function of radius and as a function of time. Can we observe these regions? Well, let's take the best images that we have from ALMA, the interferometer, and here I like to show illustrations from surveys done with the highest resolving angular resolution with ALMA, showing some of the large disks with these beautiful structures, but all the way to, and I like that we don't forget that, because usually in talks we always see the most beautiful large disk with a lot of structures, but we shouldn't forget that many disks at the same age, roughly the same age, they are very small. You see, they are very tiny compared to these ones. And so ALMA is showing us that there is a huge diversity even there of structures and sizes. Now, if you zoom in on one of these images and you're looking compared to the distance of Jupiter, 5 AU, you see this is the ALMA resolution. So essentially, the solar system scale, the inner solar system scale is extremely small, even at the highest spatial resolutions that we can get with interferometry. Now, exciting discoveries in the last few years have been to directly detect planet formation in the outer disk, so either with direct imaging or with kinematic information. But the big puzzle of the inner disk planet formation still remains. These inner regions are essentially invisible to ALMA, unreachable, the inner few AU. And that's where the most common type of exoplanet super Earths are. So what do we do? Protoplanetary disks have, on top of this story, they have extremely complex and stratified structures. As Peter was saying in the introduction, there is not a single instrument that can tell us the whole story. And in this beautiful illustration from a recent PP7 chapter by Miotello et al., you see this illustration where they combine together the gradients in temperature from a hotter inner disk to a colder outer disk and mid-plane, gas density that increases. That increases towards the inner disk. The gas density is at the lower bottom of this image. And from this side of the image, you see how they sort of qualitatively illustrate where different techniques can show us different parts of the disk. So in the gas, you can study in different lines, you study different regions, from the hotter inner regions with higher energy lines to colder regions with lower energy lines. I will show a lot of them. And from the point of view of the dust, you use, even there, you move from shorter wavelengths to longer wavelengths with a gradient in temperature. The shorter wavelengths are sensitive to the inner hot regions, and the longer wavelengths to the colder outer or mid-plane regions. And again, on top of this complex stratified structure of disks, there is also wind make it even worse. Why do they make it worse? Because you can imagine that, again, on top of this stratification and strong gradients in temperature and density in the disk, there will also be strong gradients in temperature, density, and velocity on top of the disk from winds. And here I show some evidence of winds in molecules. This is from ALMA, CO, for an earlier type of disk. And here for the classical protoplanetary disk, what we call class 2 stage, where with MUSE, they spatially resolve atomic outflows. And here this nice illustration shows the combination of ALMA and these atomic traces of outflows. Remember that in these images, when we talk about the inner planet-forming region, we are talking about the inner few pixels in the ALMA images. So these scales are very large, but we want to zoom in very close. And we have seen that we cannot see that. Even with the highest spatial resolution, we cannot zoom in into those inner regions with ALMA. So how can we see something we cannot see? I like to say it this way. We use spectroscopy. You take a piece of glass. It's really literally a piece of glass that I took in my office in Arizona. You place it under the sun and you disperse its light into colors. And now just a very beautiful image. This was done still in Arizona with the National Solar Observatory at Kitt Peak. Spectra show us a treasure of information about the gas, the temperature, the density, and kinematics, and pressure, and a lot of other things about gas in space. And this is our sun. So we can study the surface of our sun through spectroscopy and looking at the line, the ratio in depth and the sizes, the broadening of these lines from the solar spectrum. So while protoplanetary disks, as I said, are extremely complex and stratified, nature helps us by with the temperatures of these regions. These inner regions are hot enough that they produce thousands of emission lines from molecules. Now, similarly, as I showed in the solar spectrum before, there was an absorption on the surface of the sun. In disks, we see molecules in emission on the surface of the disk. And these are extremely rich, and I'll show some examples later. At the same time, in addition to thousands of emission lines from molecules, we can also study, when we have very high resolution, we can study the complex kinematics of the gas. And here is a beautiful example where there is a little bit of everything going on. So I'll show you a little bit here. So we can detect broad emission from the disk. We can detect additional narrow emission that may come from the surface of the disk, and the broad emission is the innermost regions. These lines are broadened by Keplerian rotation. So keep in mind during my talk, and I'll show that later too, the broader line means that they are closer in to the star, and narrower lines, they are farther out. But also you see all these absorption components at different velocities. So now if lines are broadened by Keplerian rotation, it's a disk rotation. So there is one side of the disk that comes towards you, one side against you. And so by Doppler broadening, the lines are broadened. But if you have a structure that is only coming towards you or away from you, you will see a shift on one side of the line. In particular, if it is coming towards you, if it is an outflowing gas that goes towards you, it will be blue shifted. And so you see here a lot of blue shifted absorption as indicating a molecular wind from the surface. And here I want to dedicate one slide as a tribute to modelers, and in particular, in this case, to the Prodimo group and led by Peter here, because really we observers are always very grateful to those who take the challenge of trying to understand the observations and model them. It's extremely difficult, given how stratified and complex these structures are. And here is just one example from the many papers that Peter has written with the Prodimo team, and just showing how with models you can simulate where different emission lines, now some of the lines that I showed previously in those synthetic spectra, where they come from in height. This is the height of the disk. This is the orbital distance from the star. And also how you can study the stratification. Now remember that I said that these are strongly stratified structures, disks. So you can sort of see the molecular stratification in a vertical sense, And also with other, now this is another illustration from other simple models. There is a lot of work on this side too. The radial stratifications on snow lines. Whenever there is a snow line in the disk, the chemical composition of the gas and dust change because one species goes from the ice to vapor. And so you can follow the radial gradients in C2O ratios in the gas and in the ice in these steps. Now, again, this is a very simplified figure, but it shows it's fundamentally connected to what we expect then for exoplanets, because depending on where exoplanets form in the disk, whether they form here or here or here, they are expected to have an elemental chemical composition different depending on their formation. Again, this is an extremely simplified picture, but we start from there. All right, so even infrared spectroscopy, this is the technique that allows us to study the hot inner region, the hot to warm, really the inner 10 AU, as Peter was saying at the beginning, in disks. Even this is a very recent field, even more recent than exoplanets. So we started having the first high quality data that allows us to draw some firm conclusions only in the early 2000s. On the one hand, we started having small samples of high resolution infrared spectroscopy from the ground, showing us Keplerian broadening of lines, so telling us that the gas that we were observing is in the disk. Keplerian broadening is again that Doppler broadening given by the rotation of the disk, one side towards you, one side against, away, and so it broadens. And from space, with the Spitzer spectra, the detection, the discovery of this amazing forest of water and organic emission in the mid-infrared. So these were the early results that really opened up the field of infrared spectroscopy to study inner disks. And now, in the past decade, we have led in the next phase has been to have large samples, so from a dozen objects at the beginning, now to more than 100 disks, and systematically at high resolution. So, and with high resolution, I'll show you better in the next slide, but these are very high resolving power that show us in exquisite detail the kinematics of the gas. So we have seen a tremendous growth in the past decade on in infrared spectroscopy, in particular in the combination of data sets, molecules, tracers, and samples to gain a broader view of what's happening in inner disk. And I'll show something, some results today. And now, as you see, we have started a new phase in this field opened up by JWST. So now it's too early to say where the revolution of that, but we are at the beginning. So these data are fundamentally understood in a parameter space with resolving power and wavelength. Resolving power is essentially the analogous of the spatial resolution in the sky, the sharpness that you can see in the sky. Now, so here is the sharpness that you can see molecular lines in a spectrum. So you see at the highest resolving power, we can resolve individual lines. As you go down in resolution, this is JWST, they start to be blended, and at the resolution of Spitzer, they are completely blended. And so you lose a lot of information. On the other axis, we have, these are infrared wavelengths, near to mid-infrared wavelengths. We have molecular traces that are spread out in wavelengths, especially water. The spectrum of water is extremely complex and is so interesting. I've dedicated essentially all my career to studying the spectrum of water since my PhD. And as you see, while water is spread out across infrared wavelengths, there are a number of other molecules that we observe. And at the bottom here, you see the telluric transmission. So if you observe from the ground, white means that you can observe at that wavelengths. Green means that our atmosphere is completely opaque to those wavelengths. So you cannot observe from Earth. So this slide is instead a tribute to instrument builders, because we need an extreme, we need to combine the best of each instrument, so where from space and the ground. Because from the ground, we can observe at high resolution, and here I show examples of the observatories and instruments, CRIRES, NIRSPEC, iShell, Vizier, but they can only observe through these small windows in through our Earth atmosphere. So the wavelength range that we can observe is extremely limited. We usually can only observe one molecule at a time, and sometimes not even a large branch of that molecule, but only a few lines at a time. Like with Vizier, we could get like 3 water lines at a time, which is it's nothing. With iShell and Cryres, we can get a broader range of CO lines, and I'll show later. Or the other option we have is to go from space. In space, we cannot get the same high resolution. We get lower resolution, but we get complete access to the complete molecular forest. Okay, so with Spitzer before and now with JWST. So what does that mean in terms of science? That essentially the ground is the realm of studying the gas kinematics from the high spectral resolution, and space is what allows you to study best gas chemistry from the access to multiple molecules at the same time, and to have a larger leverage on the excitation of each molecule. And this is why we put together this initiative that started when I moved to Texas State University. It's called SpectroDisc. It's available online, and I'll make a short demonstration now. And our motto is essentially why should you choose between instruments, and why should you choose between high resolution or spectral coverage? Just get both if you combine the data from different instruments. And this is a tribute to the team. This is the core team that built this fantastic tool. And I want to demonstrate it in 2 ways. First of all, let me show you an interactive plot of, so here it is. This is the plot showing the data that are on SpectroDisc for the same disk. I cannot say yet which disk because the MIRI spectrum is not published yet, but it's the same disk as observed with different instruments. And I want to illustrate a couple of interesting things here. First of all, the improvement from Spitzer in gray to JWST. So if you're ready, boom. This is always impressive, even to me. So this was Spitzer, same disk, same wavelengths. This was Spitzer, and this is now JWST. This is not a model. This is how the sharper view of JWST to see and study water emission in this disk. This is amazing. Now again,
sorry, Andrea, is it actually vertically shifted, or
was
it actually brighter with Spitzer?
No. Sorry, it's vertically shifted for clarity. Otherwise, okay. Very good point. Yes, it's vertically shifted just for clarity. But now that you all have seen the beauty of JWST compared to Spitzer and the gain that we get there, let me tell you why we still need ground-based. So let's go at these wavelengths. In gray, we have an iShell spectrum from IRTF in Hawaii, and in black is still MIRI. So let's zoom in here. And I think we need to zoom in a little more to better appreciate. Right. So this is MIRI in black, and this is high resolution from the ground in gray. So now you see that with MIRI, while we gain in spectral coverage, we lose a lot of kinematic information that is essential to study the kinematics of the gas and even distinguish different lines. So you see, this is a single blob. This is a single feature in MIRI, and it's composed of 3 lines when you go from the ground. And these are 2 CO lines and a water line. There are water lines here at these wavelengths and CO. So it's a mix of water, CO, and water from different raw vibrational branches. So this is to demonstrate why we need to combine different instruments. And there is other beautiful things that you can see, the beautiful bracket, hydrogen bracket series that we can combine, again, for the same disks. We can study all the way from the bracket series in the near infrared all the way to hydrogen lines in the mid infrared. So it's really amazing. But I'll stop here. I forced myself to give only a very short demonstration. And now online on SpectroDisc, this data is all available to everyone. It's just online. If you type spectrodisc.com, you get to the homepage. This is the homepage. You see some numbers just to illustrate what's included. You can select, if you like, from the homepage one of the instruments that you're interested in. You could click on iShell and you get to the Explore Data page where iShell has been selected, but you see you can also select and deselect from here. There are a lot of gadgets here that have been built by the developer team that I'm very proud of. You can get rid of instruments that you're not interested in. for instance, and you can add columns. For instance, you want to see by distance and you want to sort by distance. So you want to search stars by distance that you are maybe interested in. You have a box here where you can search stars by your favorite name. So imagine that you know all the 2MAS codes, so you can use 2MAS. If you know the Gaia codes, you can use the Gaia. I don't expect anybody to know them by heart, but if you know the HD numbers, you can use those. If you know the whatever Taurus, if you go by star forming region, etc. So you can search and see if the stars disks that you're working on have data and which data they have. So here the purpose was to combine all the available high quality infrared spectra. Well, with variable quality. Some of the instruments are not that high quality, but some are. CRIRE, SEICHEL are extremely high quality. MIRI, of course, we have 1 MIRI spectrum now, and the sample will grow very soon. And we also are adding some gadgets for, eventually we want this to become also an educational tool for students. So imagine you are a new student who knows nothing about molecular spectroscopy. You want to learn what you see here. And so here we are building a tool that is connected to the HeatRun online database to show you where specific molecules are. Now, if you do water, it's overwhelming because I told you it's extremely complex. There are thousands of lines that can emit at these wavelengths. But let's imagine we go back to, let's do, I don't know, 90. Let's get the iShell spectrum. And glitch. Oh, there. And then CO. So you want to see the CO lines, and then you zoom in, and then you can see your beautiful CO lines. And even, you know, if you go with your mouse, you can see which lines they are. This is still work in progress. This tool is just a very first version, but this is just to show you that we want to make it a sort of a laboratory online for molecular spectroscopy, and at the same time give maximum access to the data. So if you like this spectrum, you can select it for download. You see it's right here, and then you can click on download now, and there it is. And then you get the spectrodis.zip file with the spectrum and all the information to use the spectrum. There is a Python code to read the FITS file. There is a TXT file, an ASCII file for human readability, but it's exactly the same file as the FITS file, the same information. Okay, so let me go back to my presentation now, and I can talk more about SpectroDisc later with those of you who like. Let me move on to demonstrate in the final 10 minutes a few results that we have obtained with combining this treasure of spectra. So one that I like a lot is how we can study by combining different molecules as observed with different instruments. We can study the inside-out evolution of the molecular content of inner disks. Let me guide you through this complex ensemble of figures. How do we know where the gas is? We know it from high-resolution spectroscopy from the ground. We observe the CO lines. These are CO vibrational lines at around 4.7 micron. We see how broad they are, and they tell us where the gas is in Keplerian rotation. So this disk, that is a full disk, is the tau, has broader lines. So there is high-velocity gas closer to the star. And you see that as we move to disks that ALMA show us to have inner dust cavities, from this one is a very small cavity, 1 AU, and this one is very large, like 20 AU. We can see how the CO shrinks. So the high velocity gas close to the star is gone, molecular gas, and CO is tracing the rim of a cavity at larger radii. Now, if you combine this information with spectra from Spitzer, and soon we will be able to do it with JWST, and water spectra from CRIRE-2, you see how the water spectrum reflects the evolution of the inner disk that we see from the velocity of CO by depleting water from the hotter lines, higher energy lines. You see that in the small cavity, the hotter lines are already gone. And even here, these intermediate energies are already gone, but you still pick up some of the cold lines because this cavity is not large enough to have depleted all the water. There is still some cold water there. And with the large cavity, instead, the water spectrum is completely flat. So all the water is gone, as far as we could see with Spitzer. Now there are new results from MIRI, JWST. But so putting together in a cartoon, we can follow the chemical evolution together with the physical evolution of the inner disk, from full disks all the way to disk with cavities. Another thing we have done very recently, given how challenging the water spectrum is, we have combined the largest data set of spectral line information for water from multiple instruments. Now you see CO as a reference from the ground, CRIRES for the 2.9 micron water, the hottest transitions, iShell for the 5 micron water lines, VISIR for the 12 micron water lines. These three are from the ground, so high spectral resolution, spectrally resolved. They show us the kinematics of the gas. And then Spitzer, that soon will be replaced by JWST, with the colder lines at longer wavelengths. And the picture that we have been able to put together is now starting to be more complete, and we start to understand the excitation of water that was very hard to understand just with Spitzer, with these blended lines. Now it's appearing with more clarity. And what we see is a radial gradient of excitation of water from the broadest lines that are here. These are the 5 micron and 2 micron lines that are the broadest at the higher energy lines. So they trace the hotter inner region. And there is a beautiful gradient that comes out from resolving these line profiles, going to longer and longer wavelengths, and seeing how they shrink and they trace colder regions in the outer disk. And so essentially, we are learning that the whole water spectrum traces a gradient of temperatures and of regions in the disk. And now we are building on that with JWST. So let me come to that, and let me show an example of what we are doing, in particular the program that I'm leading. I proposed in cycle 1 to do a program focused on answering that question that I posed at the beginning, focusing on the process of this large-scale drift of icy pebbles that move towards the inner disk and enrich the inner disk with water. Is that happening or not, and how, in which condition that process is happening? So what did we do? There was a signal that appeared. This was a paper in 2020, Banzatti et al. 2020, where a signal appeared already from the blended Spitzer lines. You see the signal is this. It's a correlation between the water luminosity and the disk radius, the distribution of these pebbles, meaning that when a disk is very large, these pebbles are trapped in the outer disk. This is the interpretation, and they cannot get into the inner disk to enrich with oxygen. And instead, the very small disks have had a lot of pebbles drifting in and enriching the inner disk. And so the luminosity of water reflects that. More water in the small disks, less water in the large disks. And this process has strong implications, also expected implications by models of planet formation for the type of planets that can form. In particular, this is work by Lambrecht et al. 2019, where they show that depending on the mass of pebbles that makes it inside of the inner disk, planetary systems of smaller or larger planets will form. Again, now if you have a lot of mass of pebbles coming in, you can form larger cores, 10 Earth mass planets, the super Earths, and otherwise only small cores. And now there is this is to show a recent work by Anusha Kalyan, the postdoc who worked with me here for the past 3 years. Anusha already published a paper and submitted a new one where she has been studying the enrichment of water vapor in the inner disk as a function of structures, gaps in the outer disk, showing that the small disks should have a strong enrichment first and then depletion. So this would be this phase. And the large disk, instead, by not feeding the inner disk with ice, they will only have a depletion of water. And we are studying that now with JWST. These are the first data. So this is just very preliminary. No, I'm not showing any results, but I want at least to show the quality of the data. This is only a portion of the MIRI spectra that we got for half of the sample. In this program, but the purpose there is to put together the information we get from ALMA for the distribution of pebbles, from high resolution CO to tell us about the kinematics of the gas in the inner disk, and from MIRI to show us about the chemistry and how that's connected to the other information that we get from other instruments. So expect exciting discoveries from that, because I think we're on a good track, and yeah. So I cannot say more yet, but you'll see soon if what we are learning there. So now let me move to more focused on high resolution from the ground in the last 5 minutes, and just show a few examples here. This is my love, I would say, in the last 10 years because of the richness of this spectra. I call it the workhorse to study the gas kinematics and the structure of molecular gas in inner disks. This is the comparison between the coverage of CRIRES, NIRSPEC, and iShell, just to show how much the improvement of this instrument. This is a single shot. So iShell, the new instrument that came online in 2016 on the IRTF in Mauna Kea, made a huge leap in spectral coverage by maintaining a very similar resolving power as CRIRES. So actually, we can get up to 90,000 with iShell, and CRIRES Plus now seems a little reduced, so around 80,000. So we are equivalent in resolving power. There is a difference in sensitivity because iShell is on a 3-meter telescope and CRIRES is on an 8-meter telescope, so we cannot observe the same targets. CRIRES can go deeper, but otherwise in spectral coverage we gain a lot. And what do we learn? I already showed the kinematics of the gas, but also another technique is spectroscopy, is measuring the offset of lines from the continuum and obtaining semi-direct information on where that gas is, not only from the broadening of lines, but from the spatial offset. And I'll show an example of what we are learning there. In addition, this is the type of observations where we have the largest samples to date. In the past 10 years, again, we have now reached samples of about 150 disks for a total of about 500 spectra. And most of this is available on SpectroDisk. There are new data that I keep observing every semester. So this past semester is not there, is not yet on SpectroDisk, but it will be as soon as we reduce the data and can upload. So from the kinematics of the gas, what are we learning? We can learn about the inner disk structure. We see very different kinematics in different disks. We see this is the same line, but in 2 different disks. As I showed already at the beginning, some of these are very broad, some of these are very narrow. Those that are narrow are associated to these inner cavities, again, as I said before, that shrink the gas that is now moving at larger radii. For these broad profiles, there is still 2 interpretations. It's either the inner disk plus the surface, or it's a disk wind. And this was seen by using spectroscopy too. You see an offset only in one direction towards the observer. That's a signature of a wind. And this was found in the narrow component on top of this broad wing. So the broad wings would mostly trace the disk, and this narrow component would instead be tracing this molecular wind flowing off the disk. Another amazing application of spectroscopy has been to follow the possible orbital movement of companions or asymmetries in the inner disk. This was work by Britton et al., where they follow the evolution of the spectroscopic signal and the CO line in this disk with a big cavity, consistent with an orbiting object. And more recently, we are following up with other interesting systems. This is a binary of Herbig stars, where we are monitoring strong changes in CO that are probably connected to the dynamics of the gas connected to the binary system. Given the richness of this data, I have invested a lot in the past 5 years on a new survey with IRTF iShell. Here, this is IRTF near the Keck and Subaru. It's an extremely compact instrument that uses the detector extremely efficiently. Those of you who build the instrument, and in particular spectrographs, if you have seen a spectrograph, this is an amazing spectrograph. It uses the detector, it packs up these shell orders in an amazing way so that you get maximum spectral coverage in one single shot. This is an ongoing survey, and I just want, so here I'm out of time, so I'll just highlight that where we are moving towards is to provide kinematic information for all the JWST disks in cycle 1. So we are so these are targets in cycle 1 with JWST. So remember, with JWST, we get the chemical information, but we don't get the kinematic information. So we are now gathering the kinematic information from the ground. So let me skip that. And again, winds, you see, I knew that I wouldn't have time to focus a lot on that. But let me close up with this statement. So can you tell what JWST is observing? Again, you study the chemistry, but can you tell where the gas, the molecules that you're observing with JWST are? And you can have situations that are extremely different. See this case where from the ground, we see that there is a strong absorption from a molecular wind, and MIRI would observe a weaker line instead of being able to tell you that it's disk emission and wind absorption. So this is a critical problem in the interpretation of MIRI spectra. And the effort that we are doing is with 3 coordinated programs with iShell, CRIRES+, and NIRSpec on KEC, we want to provide high resolution CO information for all cycle 1 targets. And this is just one example of these CRIRES+ programs. And this is the main collaborator, Sierra Grant, there in Europe. So it's a neighbor of yours. And an example of the spectra that we are getting with CRIRES+. And here I'll close because I promised to not go over time. So thank you.
Okay, thank you so much, Andrea, for this very nice talk. All about spectroscopy and molecules you always wanted to know, never dared to ask. So this is now your opportunity to ask Andreas something about molecules, spectroscopy, inner disks.
And sorry if it was a little overwhelming. These data are extremely rich. So I try to, I still want to show you the richness and the beauty of the data, but also try to condense a few messages. So it's always a struggle to find a good balance. So I hope I didn't overwhelm you, but please ask questions. I can show you more or explain better.
So I was very fascinated by the online tool that you created. And I wondered a little bit more, can you explain how you collect all the data, who's reducing all the data? It sounds like a lot of work.
Yes. Not only, so yeah, so let me say a few things briefly, and then later again, if you want, I can give you more details. But essentially, the big so this project has been so this project has built on a heritage, a legacy of 10, 20 years of spectroscopy. So the point was when I started my professor appointment at Texas State, I realized that I was the only lucky postdoc the only lucky person who in my postdocs I had access to some of the best infrared data sets, but I was still the only one. So I had access to CRIRES survey and NIRSpec survey, and then I started an iShell survey. But these surveys were still in individual hard drive or in individual people somewhere in the world. So I told myself it's not possible that this richness is not available to everyone. And I had this idea that now I can say I had no idea how technically challenging it was, but to put everything together into an accessible database. Okay, so your question essentially has 2 answers. First is the processing of the data, the reduction. Now you have to, of course, collect the data, observe, collect, reduce the data, and make sure that you have high quality on all the different instruments, and that's already a challenge. And I can tell you already immediately, we don't do it in-house. So I get data sets from individual observers. I try to get the best. And so for iShell, I can tell you we give very high quality. So we are responsible for the quality of the reduction of the iShell spectra. But for NIRSpec, for instance, I received those from Caltech, from Jeff Blake at Caltech. I rely on their data reduction, on their quality assessment and everything. CRIRES from Klaus Pontoppidan and STSCI, I rely on their own quality assessment and data reduction, which I know is good. So we put together these data sets, and then it comes to us. And as internally, the other issue that required 2 years of work was to be able to build a database that is flexible enough to take very different formats of data, link them together, make them into a single format, and deliver it on a website that is fast. And I tell you, it's not how quick this is. if you play with it, you see that it's very fast depending on your connection. But no, there is only one type of spectra that is slower. It's the Eigen spectra, because they have so many pixels that it takes a while to load them. But otherwise, it's extremely fast. The genius, the wizard, I have to say, and I want to say it, the genius behind this is this person here, Caleb Wheeler. So he's a professional astronomer, but he's a multiverse person. So he builds instruments, and he is also a software developer. So it's one of the most complete professionals that I've seen: a scientist, instrument builder, software developer. And he is the mastermind behind the complex forest structure of the database itself. And these are instead computer science students from Texas State University who have mostly built the interface online. So this has been an adventure. Every time that we get a new student, I always ask myself, well, how will this end, right? Because every time you get a new person with new ideas, new skills, and it can go bad, it can go well. I have to say, with these people, it went very well. We were very lucky. We got people who gave generously and a lot of talent and made possible what you see now online. So
so it's actually a follow-up question. So how do you manage? You know, you have to rely on so many people, because you as you say, you only contribute personally with a few, but you rely on many other people. How can you make sure that they actually deliver this to you on time? For example, I would be interested concerning the mirror spectrum, because this is for me, this is the most easiest interface to get a mirror spectrum. I go to this webpage, and okay, there's only one at the moment, but I'm sure this will change very soon. So my question is about the delay. So how long will it take you to upload the MIRI spectra, and how do you manage that the people actually who have the data send it to you?
Yeah, so here this is a lot of personal collaborations and emails that I send. So you see, by now we have, 8 spectrographs, and I believe we started with 5. So already we have expanded since the beginning. I emailed the people of Igrens. They are at UT Austin, so they are my neighbors, like half an hour north from where I live. And I told them, look, you have a fantastic spectral data set. You want to host it in a place where people can access it in an easy way? And they said, well, I think it's a good idea, because they have their own archive, but it's extremely hard to access. It doesn't have a GUI. You can access, if you know where you're going, you can take individual files, but there is nothing that is as fast as this and allows you to interact with the spectra in live. Now, so you see, let me show you an example of the Eigen spectra. I don't even know what, oops, there is a glitch here. You see, live demonstrations always have some problem. I don't know why the Simba name is not showing. Okay, this is a tau. So why is it not? Let me do df tau. Oops. All right, there it is. So let me do this. Let me unselect. Let me do df tau. Okay, right there. No, that one doesn't have. Let me do RU. No, what was that? FC tau. I don't know. Eigen spectrum. Okay. So you get there, right? So you can see now those bracket lines. You can see the beautiful CO lines, and the Eigens people were very happy to have something like this in place for them. And I have ongoing conversations with people with the X-shooter spectra, for instance, HST COS. We can expand very easily to any other wavelengths in spectra. So the two fundamental types, the two constraints we have for this database are that it must be spectra, so we cannot host images, and that it's about planet-forming disks. Okay, so in principle, you can put any spectrum here, but if you put the spectrum of a galaxy, then it doesn't make much sense anymore. So with these two constraints, we can host any data from anybody. And so to add a new MIRI spectra, I can tell you it takes 1 day. And 1 day just because it's human. No, we need to have the time to take the new spectra and upload them. but the Caleb Wheeler built this in a fantastic way. It's extremely fast to rebuild the whole database from scratch. Whenever you add new data, in 2 hours, you can rebuild the whole database and deliver it online. So we can do it overnight from one day to the other. And how do we get people to send us the data? For instance, the MIRI spectra, we have a lot of direct access to now my program of MIRI, and we have a few others that are collaborating with that I'm part of. That we will deliver up to 30 high-quality MIRI spectrum by the end of the year, I believe, as soon as we publish them. So at least I would like to publish one paper and then I'll deliver them. But for iShell, as soon as I observe them and we have time to reduce, I publish the spectra online. So in fact, here, if you go to iShell, you will see that there are spectra that I haven't published yet. And as we observe, we put them online.
Okay,
So
maybe one more physical question.
Yeah.
So you said you can actually trace the water with, by excitation energy. So you can see that certain lines appear first or disappear first, etc. I would like maybe if you could comment on these latest JWST results for this brown dwarf disk, where apparently there's in one of these disks there's an inner zone which is very, very carbon rich or completely water poor, so it doesn't have water lines, but it has this booming C2H2. So you had this idea of the pebbles that are going inwards and then they actually liberate water, but I think what we need now is also to think about that pebbles are kind of collecting the water somehow, but they are stuck then dynamically, so they don't go further in. And so this might be a way to explain why you get this extraordinary spectra where all of a sudden the water is missing. So I wanted to ask you whether you have any clue how to explain that.
Yeah, so the story, yeah, it is indeed that, right? So that if we can lock those pebbles outside and trap them into systems of rings, there should be less water in the inner disk. We are testing that now with actual spectra. Now, on top of that, there are other effects. So I had another overwhelming slide that I didn't show. It's the correlations between water and other molecular line luminosities and a number of stellar and these parameters. You can if you look to in my 2023 paper, I show an ensemble of water lines and how that looks. But water has a dependence on, and other molecules has a dependence on multiple parameters. So it's not only the pebble distribution, but it's also the depletion of the inner cavity, the stellar luminosity, and even more the accretion luminosity. So now you're working in a multidimensional parameter space where you're following the behavior of one molecule over another, but you have to carefully go in this multidimensional parameter space and understand all the axes before you can make strong statements. And this is not easy. And we are working on that right now. So I'll be able to tell you more in maybe in a month from now. But it's an extremely challenging but also exciting problem, because indeed, if you look, even if you look at this spectra only, these ones, you see what a diversity of the organics, for instance. Look, this one is very strong in CO2, and there seems to be maybe a gradient here in HCN, but C2H2 not so much. It goes down and then up. And CO2 in particular is puzzling because it doesn't really follow what the other organics are doing. So there is a lot to discover there. And I think the MIRI spectrum will indeed show us very exciting discoveries in the next months, even just in the next months with the data we are getting.
Yeah,
I had two questions. I don't know if it's ending now or.
Well, I think it's now already 5 minutes past the hour. So what maybe can you join the after discussion? So we will basically. I will first let me stop the recording. Yeah.